And so I want to pick up where we left off, as promised. I'll walk us through a couple of translations of the ordinary lambda calculus into pi and rho, because I think that's useful and illuminating for folks. Hopefully, if you're a developer by now, you have at least some exposure to the lambda calculus and you understand why it's important. Functional languages like Haskell and Lisp and OCaml and Scala and yada, 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 they all enjoy the title functional because at their core is an implementation of the lambda calculus. So the lambda calculus can be thought of as the center or the core of any functional language, and that's what it means to be a functional language, is that you take as your core model of computation the lambda calculus. So that's partly why it's relevant to us. So let me go ahead and do a screen share. But the other reason, as I mentioned, the larger goal is we're investigating the parsimonious lambda calculus, which is a flavor of lambda, because Damiano Mazza has been able to develop the Cook-Levin theorem inside the parsimonious lambda calculus, and all zero knowledge stuff basically goes through Cook-Levin. So we're interested in it from that perspective. One practical import for us is that we can, with an appropriate encoding of the parsimonious lambda calculus, we should be able to get ZK snarks directly into rho-lang through rho, which is of interest, I think. Okay, so let's take a look. So here's a reminder of the syntax of the lambda calculus. So you have variable mentions. So it's the use of a variable in some position, either as an argument or as a function. And then there are abstractions. So we turn an expression which may use mention A into a function which is waiting for an A, and then we'll evaluate M. Or we have application. So we apply some term which hopefully ultimately becomes a function to an actual argument. So that's the lambda calculus. Very, very tiny, or that's the syntax of the lambda calculus. To make it complete, you need to add alpha equivalence, which says that if we consistently turn all the A's into B's, then this is the same term as lambda B dot M, where you have B replaced A, assuming that we haven't captured a free name. So if B is free inside M and we do this swap, then that's not going to be the same term. But if B is fresh or distinct from M, then if we swap A's for B's, then this is exactly the same term. And then you need beta reduction, and beta reduction says if you have a lambda in the head here and you have some other term in the argument position, then that reduces to M, where every occurrence of A has been substituted by N. So syntax plus alpha equivalence plus beta reduction is lambda calculus. So teeny tiny language, and astonishingly, it's Turing complete. And then refreshing the pi calculus. So this is the synchronous form of the pi calculus. I'm not using Milner's notation. I'm using a notation that's closer to rho, but it's the same. It's the same construction, right? So you've got listening on X for Y and then do P. You've got send Y on X and then do P. So, and then you have a fresh name construction P, and then you have parallel composition and you have replication. So this is That's the syntax of the pi calculus. The structural equivalence includes alpha equivalence. So every binder, and there are two binders. Here's a binder and here's a binder. So wherever you have binding constructs, they're subject to alpha equivalence in the same way that lambda is subject to alpha equivalence. And then you also have an equivalence that makes this together with that commutative monoid. So P par 0 is the same as 0 par P, which is the same as P, and P par Q is the same as Q par P, and the operation is dissociative. And then you have some equations around nu. So nu x P is the same as nu x P, nu y P is the same as nu y nu x P, and then you have extrusion, where if Q doesn't mention, so if you have nu x P par some Q, then if Q doesn't mention X, you can move Q under the nu scope. So that's extrusion. So that's the whole calculus. It's not as tiny as the lambda calculus, and more importantly, it's not higher order. So lambda makes all lambda terms, including functions, first class, and pi calculus does not. You can't ship processes around, you only ship names around. So before I go into the translation, any questions about what I just said? That should all be bog standard by now.
Yes, this is clear.
Okay, all right. So, if it's not clear, my recommendation is ask questions and get to the place where that is crystal clear, where that part is like, having cereal for breakfast or something. It's really.
Yeah, I mean, one thing I'm wondering is in terms of how you write all these equivalences that you just talked about. In some ways, I look at them as like constraints on this first or this one-line syntax you put here, right?
Yeah.
And why is it that writing those constraints is not important? Is what I'm wondering. Meaning,
oh, it is important. It's just that it's so commonplace. I mean, I've gone over this so many thousands of times that it's just going to muddy up the presentation.
Okay, I see.
But so the big picture view, which is relevant for understanding operational semantics and logical form, all of that stuff, is is generators and relations. So in mainstream mathematics, we have this idea of presenting an algebra via generators and relations. So you present a monoid in terms of its generators and some, so you have some atoms, for example, the natural numbers, and you have some operation like addition or multiplication, and that's going to give you the free gadget. So with no constraints, you just generate the language, the syntax. But you don't really have the essence of the construction until you add some equations. In the case of the monoid, the equations have to do with the identity, making sure that it's an identity on both sides, and associativity. So generators and relations. So the same thing is going on here. Generators, and then the equivalence we talked about are the relations. The big difference between these kinds of constructs and classical mathematics is the reduction rules. So classical mathematics talks about generators and relations as a part of your basic data type. Computer science talks about generators, relations, and rewrite rules. So there's a third thing, and that whole thing is a package. And that's very different from mainstream mathematics. And the reason it's different is ultimately this boils down to how you look at things from the perspective of category theory. Monoids, groups, rings, fields, vector spaces, modules, blah, 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 blah. All of those data types, when specified in mainstream mathematics, have no dynamics. They don't represent the dynamics. What you do to get the dynamics is you have some kind of morphism, some kind of structure preserving function. So for example, in the case of groups, you have group homomorphisms. In the case of rings, you have ring homomorphisms. In the case of topological spaces, you have homeomorphisms. So there's some kind of structure preserving function, and that's where you do the dynamics. And so typical categorical constructions will be our objects are blah, 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 groups or rings or fields. And our morphisms, like in the case of vector spaces, are linear functions, right? That's vector spaces and linear functions is a typical category. That is very different in packaging from the way computer science does it, because computer science, at least in this flavor of computer science, is packaging the behavior along with the data type. This is a very, very big difference. And the reason it's so big is because if you wanted to build a category of pi calculi-like things, then the objects are going to include the rewrite rules. And so now you have to ask, what are the structure preserving morphisms? And what does it mean to preserve rewrites? So this is why if you go to the literature, you do not find a good impedance match between these kinds of computational gadgets and category theory. There's a lot of work to get it done, but and Milner's bigraphs is effectively the first real foray that respects all the things that need to be respected. But in general, this is still a wide open field at the intersection of computing and mathematics. So that's at the heart of your question, Rao, right? If I take your question seriously, all of that is at the heart of it, but I typically don't want to go into all of that because it's a whole big discussion. So either we kind of go, well, you know, the equivalences are the standard equivalences that everybody should know, or we take it really seriously and we talk about the shape, you know, how this is related to classical mathematics and how things are different. Sorry for the long-winded.
No, that's very helpful to understand. Thank you.
Sure. Okay. So
can I just ask you,
yeah.
How can I see axioms? Are there represent maybe similar thing to this equivalence?
So the axioms are so there's two levels to your question. First, the axioms are that are specific to these systems are the interpretation of the expansion of the grammar, right? So how do I go from this finitary thing to the infinitary thing, which is the language? So that's one pile of axioms. And then you have additional axioms that are the relations. And then you have additional axioms, which are the rewrite rules. Those are the axioms of these systems. Does that make sense?
Okay. Yes, thanks.
Okay. The deeper level is that all of this is taking place, the interpretation of this is taking place against some backdrop of some foundation of mathematics, right? So if this thing is generating something, is it generating a set or is it generating some other kind of collection? This is where category theory really starts to help, because if we connect this to a Levier theory, then we can associate this with a monad, and then the base of the monad does not necessarily have to be set. It could be something else, like vector spaces, as an example. So there's a deeper thing here, which is what is the foundation of mathematics against which you are interpreting these generators and relations and rewrite rules? Part of the whole thing of operational semantics and logical form is to get really crisp about all of that. Does that make sense?
Yes.
Okay. All right. So back to our regularly scheduled program. So this is Milner's translation. In addition to rewriting the syntax of the pi calculus slightly, very slightly, I also didn't include some of his syntactic sugar. So in his functions of processes paper, which I heartily recommend, if you don't know that paper like the back of your hand, you are doing yourself a disservice. That is the first published account that does the whole generators and relations semantics for the pi calculus. Prior to that, they were like the Milner, Perrow, and Walker paper give a labeled transition semantics for the pi calculus. So functions as processes is a pivotal watershed moment in the development of computing. But he does do a lot of side notation, is like syntactic sugar, which in his mind makes it easier to write things down. But I think for the lay person, it actually obscures things. So I have eliminated all of that. It's still a very tiny translation. So let's go through it. How does it work? If I have a variable mention, then what I do is shout along a name associated with that variable, the channel U. So the translation is taking a pi calculus term and a channel as a parameter, right? So if I'm evaluating a lambda term and it is a variable mention and I have given the channel U, then I just send U along A. That should be clear. Now, if I have an abstraction, the way that's going to work is, the interpretation of some abstraction lambda A dot M given U, I listen for A on U, then I listen for the next place to pick up, the next channel to pick up the interpretation. And then I run M under this scope where A is now bound, picking up the interpretation at V. So V is the next channel where we continue our interpretation. And then, go ahead.
Can I ask you, this is a little confusing to me because we are waiting for two values on U. And,
that's right. So it's just sequence. Do this, then do that.
Sequence.
Yeah, just like the Rolang 1.1.
Oh, I see. And
yeah.
Why not use a tuple to receive both, or basically?
I'm trying to be as connected to the pi calculus as possible.
Okay.
But your point is actually well taken. I should do it this way. ... Right, so that you're not surprised by the semicolon notation.
Oh, I see.
Okay. So first I listen for A on U, and then I listen for V on U. So what this is going to do is it's going to give me the value for A in this thing, and V is where I'm going to pick up the continuation of the interpretation. And then application is where we wire these two together, right? So suppose I had a lambda A dot M applied to where M is an A applied to, some variable. So first I make a fresh V. I'm going to evaluate the function in using V. So hopefully this gives me a lambda term. I'm going to run that in parallel. So then we're going to wire up the evaluation of n in such a way that this does in fact become a argument to m, right? So we know that m is going to pick up its arguments from v, right? So that's here. So in order to do that, first we make a fresh x, and we shout x over v, then we shout u over v, and then we run the replicated form of this. So this you get as many copies of this as you need. And so here from x, we're going to get w, and then we're going to run in, we're going to evaluate n using w. So it's a little bit tricky. It's a little subtle. You know, Milner is known for this, for the subtlety of his thinking. So let's run an example. So let's run lambda a dot a applied to n. So we know what that should be, right? So if I substitute n for a in a, I should just get n. Yeah?
Yes. Mm-hmm.
Okay. All right, cool. So using the last line of the translation, let's remind ourselves of that, right? So that's this one. We evaluate, we make a fresh v, we evaluate the m term, which is lambda a dot a, using v, and run that in parallel with making a fresh x and shouting that over v, and then shouting u over v, and then from x getting w in order for n to evaluate to w. All right, so the first thing is that we can go ahead and evaluate this. So that's going to be, again, listening for a on v, listening for w on v, and then evaluating a using w. So let's just double check that, right? So this is a lambda. So in this case, v is our u, right? So the parameter here is v. So listening for a on v, then listening for, since this is a v, I replace this with a w, and then do the final thing in terms of w. Right, so that's what's going on here. And then we evaluate a on w, but we remember that that's just shouting that, and then this I've just left as it is. And then this thing is just shouting w on a. Okay, so we've completely translated that part of it, right? And now, and we don't know the structure of n, so we can't go any further with that. So this is as far as we can go with that. But we do have enough to actually execute. So using the extrusion relation, I can I just visually inspect, is there any x's mentioned here? No x is mentioned. Awesome. I can pull the x out to the top, right? So now I've got new v, new x, and then this is in parallel with this. Well, lucky for us, look at that. I'm shouting x on a v, and then I'm shouting u on a v. So that's these two things. They kick off these two things, right? So I'll just get whatever the substitution is here in parallel with that under this new scope. Is that clear?
Yes, yes.
Okay. So, so that's just a shouting x under new v, new x. And look at that. This x is that x. And so this w becomes that u in u. Oh, this is a bug. This should be u. Sorry. So now see what we've got. We in order to run this, we had to fork off a copy, leaving the other one, leaving the banged thing around, right? So we would, I skipped a step, but we fork off a copy. We have one of these 4s in parallel with the banged version of the 4. It interacts with the X, we get the NU here, and then we get the remainder. Now, notice that without loss of generality, N doesn't mention X, and N doesn't mention V. So the nice thing is I can move these over to here. And now I've got a new scope guarding this input, right? So this can never, ever interact with the outside world, right? This in particular can't interact with N, but it can't interact with the rest of the world because new guards this. So there's no way, it would have to send it out, but it can't because the only thing it does is listen. So this is garbage. We can garbage collect that. And likewise, this new is not covering N, and this V is not mentioned here. So that's also, that it can be garbage collected. So this is equivalent to that. So you see, we went from lambda A dot A applied to N to N.
Yeah, this is very nice. I mean, this is somehow in the spirit of lambda calculus. We are creating some variable in some scope, and then we can eliminate this variable after
Correct.
abstraction.
That's exactly right.
Yeah.
Okay, so this is a lovely translation. Now notice, this is the reason why I wrote the pi calculus in rho style, is because this translation is also a translation into rho, as long as you just decorate all outputs of names with a star. So in particular, if we just put a star here, here, and here, this is now a translation into the rho-calculus, right? So that goes back to if I make this star here, this is really just rho. This is syntactic sugar. It can be eliminated. This is syntactic sugar. It can be eliminated, but we're safe to put it back in. So that's rho. Cool, huh?
Yeah.
All right. So we went from a translation of lambda into pi directly into rho. So we get to just use Milner's translation. However, for fun, there is a different translation that is more direct. Now, I haven't done any proofs on this. I just sketched it out, and I'll show you a calculation. So, I mean, a lot more work needs to be done to make sure that this is correct. But I just want you to, get a feel for, a flavor for how you might use the higher order nature of rho in order to do things. Okay, so here's the trick. We're going to interpret mentions as wires. So on U, I get the value, and then I just drop it in place, right? Just there it is. You gave me the value, so I give you the value, right? So this is the linear logic approach, right? Variables are wires. Okay, so then the abstraction. I'm going to listen for A on U, and then I'm going to make a fresh V where I put the value and I interpret M in terms of the V. Okay, so I've basically made an association between. The way to think about this is it's like making it like this is standard in implementations of functional languages, and also languages like C. So you go from variables to locations, and locations to values. So locations are kind of your abstraction, right? They're they're like normalizing your variable names or something. Does that make sense? So you have the variable that's in your program text, and then you have a location in some data structure, and then the location tells you how to get to the value. So that's what this is doing. Is that making sense?
Yes, to me.
Okay, cool. All right, and now we wire these two together in the following way. So I interpret M using U, and then I put that in parallel with, well, just go ahead and interpret N under some fresh V, but shout it down U. So I'm using the higher order nature, right? Now I can grab this thing and just it's a whole process, right? So I mean, like, you see the simplicity, right? This is so much simpler than this.
Yeah.
It's a lot simpler. Okay, so okay, so now
basically we don't.
Go ahead.
I'm thinking we don't need to create these additional names to send stuff around. We can just directly send this the whole expression.
Yeah, you send the whole expression, exactly. Yeah. All right, so now let's see what happens. Okay, so again, we'll calculate lambda a dot a applied to n given u. So that if again, look at our translation, we interpret M and run it in parallel with shouting something down U. Okay, so interpret N given U and run that in parallel with shouting this down U. Okay, very straightforward. So when we interpret this thing, so this is listen for A on U, and then new value of A, interpreting that. So I did it in these steps rather than running this to ground, because we know what that is, right? We can go ahead and evaluate this right away. Why? Because I've got a shouting of something here running in parallel with a for comprehension over there, right? So I can go ahead and do the substitutions for A, right? So that will put this in place of the star A right here. And then I can go ahead and expand this out, right? So I expand this out to the 4A, and we notice that the new scope is over the entire thing, right? So we can still do the evaluation. So now I run this shouting of this thing against this listening on V for X. That's not for X, it should be for A. And so what will happen is we'll just put this thing in place for the star A. So now we get new V in using V. That's just new V in using V, which is the expression. You see, it's much simpler, like half again simpler. So we went from, in fact, it fits on a page, right? Here, we have to go over 2 pages before we get to the completion. And here, we go from the original thing in just a few lines down to the evaluation of N using V. So that's, my recommendation is, if you're interested, go and play with this translation. It's relatively straightforward, but it gives you the feel for how you can use the higher order stuff. Now, where do we want to go? Well, so if you recall, the parsimonious lambda calculus has lambda in your affine variables, A, B, blah, blah, blah. and then you have some tensor expressions, and you have exponential variables, expressions in the exponential variables. Now, if we were to naively attempt to use the translation that we had before, we run into a problem. And the basic problem is that N is only waiting for V and doesn't know about the fact that we need to bifurcate the namespaces. So here for the tensor, I need a version of U that is separate from the version of U that's over here. And here, this thing doesn't know that we need to do the bifurcation. So you have to separate the namespace in some way in order for this to work. So that approach will not work. And what I'd like to do is to give everyone a chance to wrestle with it for a week. What would you have to do in order to make the tensor work out? And so there are several ways to solve the problem, but you have at least at your disposal, you can get the Milner translation factored through rho, right? So you can use this translation as the basis, or you can try to modify this translation so that you support what's going on here.
Yes, nice.
Okay, so I'll present a solution next week, but I want to give everyone a chance to dig in and come to grips with the material. It's not hard, but it requires, you know, just a little revision to the way the interpretations work, so that you support the tensoring and you support the streams. And once we're there, we're most of the way done. The trick is we can now take all of the encodings that Damiano Mazza gives via the parsimonious lambda to interpret circuit value and circuit evaluation. In the parsimonious lambda calculus can now be ported directly to rho-calculus. So
it looks very simple.
Good. Good. Well, I'm looking forward to several solutions.
Can you just give us a hint for streams? Are there? I'm thinking about like nesting.
That's one way to do it. Yeah, you can do a nesting.
Okay.
You can do a nesting for sure. So in fact, that works very nicely, because what you do is you have a finite prefix, right, where the values are different, and then after a finite number of times you have to do a recursion. And so the only way you can change the values with the index, which would be, you know, something you could pass in the recursion.
Okay.
Yeah, does that make sense?
Yes.
Okay.
I mean, tensor seems like easier.
Tensor should be easy.
Yes.
I can give you a hint. The one way that I worked out a solution is to you can build lambda over rho, where you have A's here. It doesn't say where the A's come from. So the nice thing about rows is that we know where all the variables come from. They're quoted processes. But here, lambda is really a parametric type. So you could parameterize it in row processes. And so then you have an operation that says, well, give me the row process that corresponds to this A, right? And then you can build up an environment using that approach. There's another approach where you build up an environment, and you build up an explicit environment, and you know how to split the environment into separate namespace, separate environments, basically. So either of those are conceptually available to you. So yeah, next week you've been given your homework.
Cool.
Okay, so in the last 15 minutes, I just want to reiterate a few things about requirements for the operational semantics and logical form. What are our sanity checks? So in general, we want a decomposition of formulae into the following components. So every formula is going to be a container of the computations that give witness to the formula. So you need formulae that arise from the container. So the most natural or most common container is set, but there should be other containers. In particular, the linear containers. And the reason that's interesting is because you want to treat formulae / types as queries. And so then when the container is updatable, that's no longer a set. So that's why that becomes important. Then you also want formulae that arise from the structure of the terms used in computation. Okay, so that's like, let me make this bigger. So, for example, in the case of the monoid, we have a formula that detects that you have a composition as opposed to an atom. So that's an example. In the case of the rho-calculus, we have a formula that detects that you have a par, or a formula that detects that you have an abstraction, or a formula that detects that you have an application. So that's important. And then the other thing is formulae that arise from the reduction, from the execution of a computation. So these are the modal formulae. All right. So that's the basic. That's number one. Then the next thing is we want a sanity check. We want the following theorem to apply or hold. All right, so the second thing is a sanity check. What we require is a theorem that says two computations, say P and Q, are going to be bisimilar if and only if they satisfy exactly the same set of types. Now, the reason this is critical as a theorem is it gives us substitutability. This formalizes Listov's substitutability principle. In order for the type system to be really useful, we're very interested. We want programmers to have some guidance from the type system.
in particular, they need to be able to know when the substituting one program for another is going to be safe. And we know that they're exactly safe. That they're going to be the same program, and for all intents and purposes, if they supply all types, if they satisfy all the same types. But you get ranges of different notions of substitutability, depending upon the types that they mutually inhabit. Does that idea make sense?
Yes, and is this something that we will do as in a compiler, or users can also do something like that?
It's a theorem that's true of the type system, so it's not going to be done by anything. Like we establish it once and for all as a mathematical theorem.
And you said when types are the same.
So what we're saying is two programs are going to be bisimilar if and only if they satisfy exactly the same set of types. So for every type T, P satisfies T if and only if Q satisfies T. So this is not about one type, this is about all the types. So typing and behavior come down to the same thing. They typing pins down your programs. Does that make sense?
Yes.
Okay, cool. So now the one thing that's really important in this that turned what was a surprise and then was resolved. So for Milner, you get exactly this theorem. So for the Hennessy-Milner modal logic for pi calculus, you get this theorem that two processes are bisimilar if and only if they satisfy exactly the same set of formulae. Then along come the spatial behavioral types, and you can easily spot that the spatial formulae can see when a process is a par, right? They have X-ray vision into the structure of a process, but bisimulation can't see when a process is a par. It can't tell the difference between the sum of all the interleavings and parallel composition. Does that make sense?
Yes.
Okay. All right. So how do we repair the situation? So what Lozes and Kyres showed was if you put actions back into the rewrite rules that correspond to the structural equations. So associativity, commutativity, if you make those actions in your rewrite rules, you get back the equivalence. So the folklore, the intuition has been that we know we can generalize this. Whatever your term structure is, and whatever equations, so back to Raoul's question about the equations, whatever equations they support, you get this correspondence. So you put the equations in as rewrite rules. So you can think of them as bidirectional rewrite rules. And now your bisimulation can see all the structural stuff. This becomes super, super important in the next phase of the program. And that program has to do with complexity. So another desiderata for operational semantics in logical form is that we can use types to, since they're completely characterizing programs, we want the types to give us information about complexity. And this is not going to happen if our types are blind to the structure, right? So Milner's logic is blind to the structure. The Kyrace logics are cognizant of the structure. And and we know that space complexity comes from the structure of the terms. That's where we're going to get the execution complexity is going to come from the rewrite rules, but the space complexity of your terms is going to come from the structure. And so if your bisimulation is blind to that, you're screwed. You're not going to get types and bisimulation giving you the same story about complexity. So what we do then is we have a generic answer to the structural component by demanding that we and through this generic answer to the structural component by adding the equations, the structural equations as rewrite rules that gets us back to the sanity check theorem that two programs are bisimilar if and only if they satisfy the same set of types. Does that make sense?
Yeah, I'm trying to follow you, and I think most of what you said I can at least parse.
Oh, okay. Well, I want to come. We're over time, so I'll stop here. But I want to come back to this because this is super important. As we move forward, understanding the desiderata for the algorithm is very important. All right, I'll leave it there and see some folks in Dev Stand Up in just a minute.
All right.
Thanks.
Thank you.
Thank you.
Great. Thank you.